So good afternoon once again. Thank you for being here. So I would also like to thank UPLB MNH for this opportunity. So my presentation for this afternoon is about the use of the different dimensions of biodiversity for us to better understand the impacts of rainforest transformations. So using species information, traits, and phylogenetic trees. So first, I will give you a little bit background on tropical rainforest transformation to agriculture, particularly to oil palm. And then I will delve on different dimensions of biodiversity and how to measure them. So this encompasses taxonomic, functional, and phylogenetic diversity. And I will present sort of a case study, which is part of my master's thesis, impacts of rainforest transformation to oil palm and bats. And I will wrap up my presentation with some future perspectives. So we know that tropical forest is the major reservoir of biodiversity. But over this past several decades, most of this tropical forest has been cleared for agriculture. In the first article, it has been estimated about 80 million hectares has been cleared way back in 1980s and 1990s. A recent article in Science shows the staggering loss of forests caused by industrial agriculture. So mostly this is for oil palm development. It's quite sad. So that article entails of how much industrial agriculture is contributing to the tropical forest loss. And the answer is some 5 million hectares, which is the area of Costa Rica, every year. And the time frame for this analysis is between 2001 to 2015. So it's expansive. So with that, most of these transformations actually in tropical regions is for oil palm development, since oil palm have this very high demand. So to put that into context, let's take a look in our day, a day in our life with palm oil. And so actually we might not be aware, but we are using palm oil most likely every day. It's everywhere around us. So palm oil and its derivatives can be found in soaps, in the toothpaste that we are using, on the food ingredients in our foods, cosmetics that we're putting on, and cleaners. So oil palm we have this very high demand for oil palm, and in consequence with that, this is the scenario. So a large area of tropical forest has been converted for this monoculture, oil palm plantations, just to meet the demand. So in Southeast Asia, this is the case. This photo is from Sumatra, Indonesia, which there you will be overwhelmed with these plantations. You can really see a vast area of just oil palm plantations. So way back in 2012 in Indonesia, which it has the highest production and plantation growth rate in the world. Now, way back in 2012, a forest of about 150, a forest of the size of 150 soccer fields has been converted to oil palm every hour. So imagine how expansive the conversion is way back then in Indonesia. And it's still happening now, currently. So with that, what does it all mean for biodiversity? So the tropical areas suitable for oil palm plantations are particularly rich in biodiversity. So it harbors a large number of endemics and threatened species. And the transformation of lowland tropical rainforest to oil palm plantations, it has gained a significant concern, especially in its negative impact on tropical biodiversity. So in here, at least, according from IUCN, at least 193 threatened species are being threatened by this oil palm development. And the proposed expansion of oil palm could further threaten 54% of mammal threatened species and 64% of the threatened bird species. And this number is much higher for amphibians. So if we look into the response in terms of species richness and species abundance, now we can see here that the response is quite idiosyncratic. So some taxa responds positively, some taxa responds negatively. So for example, for bats, Now there's a decline in species richness, but there's an increase in species abundance, which is caused by these generalist species. So there's one or two species that have very large numbers present in the outcome. So in this graph, the arrow tail is intact forest, and the arrowhead is the outcome plantations. So you can see here, for example, the bees. There's an increase in species number, but there's a decrease in species abundance in the abundance. So it simply tells us that relying mostly on the taxonomic level of diversity, taxonomic metrics of diversity is quite, we should be cautious with that. It is idiosyncratic, so it depends on the taxa being studied. So with that, we need to explore biodiversity response beyond this level. So here comes the multiple facets of diversity. So in terms of traits, functional diversity, and in terms of evolutionary histories, phylogenetic diversities. And this is vital for conservation prioritization, incorporating these three dimensions of biodiversity. Though what we are doing, most of our research is we are more focusing on taxonomic measures of diversity. So functional diversity, it refers to the variability of ecological traits present in a community. And phylogenetic diversity is the differences in the phylogenetic histories present in the community, and the different distinct lineages present in the community. So these are I will discuss first the first component, taxonomic diversity, and this is a hypothetical scenarios case in which we convert forest to outcome. What would be the response? So in terms of species number, we could see that when you convert forest to outcome, there's a decline in species number, and that species could have a high number of high level of abundance. In terms of relative abundance, now we can see that some species could gain more abundance as compared to other species. But then again, if we look into the previous figure, this response is quite idiosyncratic. So we should be cautious in interpreting this response. And we have this diversity measure, Shannon Diversity Index, Simpson's Diversity Index, and most of our research here would delve on biological assessment. We are using these indices. But we need to be cautious in using, for example, Shannon diversity, since it's a function of species richness and species evenness. So somehow it has this non-linear property. So to illustrate that, for example, we have this community 1, we have species number is 4, community 2, species number is 3, so which is more diverse. So it's the first community. For the second scenario, species number, for the first community, we have both communities have the same number of species, but of different levels of evenness. The first community is uneven, and the second community is even, so which is more diverse. So based on Shannon entropy metric, it's the second community which is more diverse. So in this case, we have high number of richness for species, but it's uneven. We have low number of species, but it's even. The question is, which one is more diverse? So this cannot be answered using the Shannon-Weiner diversity metric. So that's why we need to be cautious in interpreting the output of this metric. And that's the sort of the constraint of more of the taxonomic research, the ecological research that utilize this taxonomic level of univariate level of taxonomic diversity measures. So most likely we have this comparable level of, or most likely the same level of Shannon diversity, but we don't know. Using this Shannon diversity, it might lead us to misinterpret what is the actual diversity value of the community in question. So to circumvent that, we have this Hill's number, or species number, equivalent number of species. So this is the number of equally common species that would be needed to give the same diversity as the community study. So in short, we are giving this linear property or the doubling property of these different indices. So if you're interested, you could read the work of Joss and Ann Chow for that. It's a good read. So we just convert these different matrices into its Hill's number for us to have this direct interpretation as compared to its raw Shannon diversity metric, which we don't know. No, it doesn't have a direct interpretation actually. So I discussed some metrics for taxonomic level and some of its utility and some of its constraints. And again, we need to be cautious with that. And to add up on that is we need to also to consider the other facets of biodiversity aside from this. So here comes functional diversity or trait diversity. So it is the facet of biodiversity that accounts for the biological attributes of organisms linked to their fitness or ecological roles, that is the functional traits. So in this hypothetical scenario, from forest to all palm, you can see here that the number of species is the same, it's 4. So maybe we could see that in terms of species richness, it doesn't have an impact at all. But if you see the functional traits, the response in terms of functional traits, what you can see are all of the species have these circle traits. So there's somehow a trait filtering. There's a particular trait that could persist in a particular converted habitat. So these subtle responses is, I guess it would be useful to capture these kind of responses. So when we say functional traits, it could be in terms of how in terms of morphological, physiological, phonological calls, for example, for bats and for frogs. Some are behavioral, some are in terms of habitat associations. So these different traits give us an idea of what is the ecological function or ecological role of a particular species in the community. Or, for example, traits that expounds how the species exploits its resources. So as a response, for example, in this theoretical graph, environmental gradient, it is different numbers with different species traits. So, for example, when we convert forest to open, you see the value there. Now, it only allows a certain number of traits to persist in that particular new habitat. So, this is the concept behind this sort of a theory. So, to quantify there are a number of metrics to quantify that. There are lots of them. In terms of convex zones, in terms of functional richness, functional deepness, functional divergence, and all of these matrices are complementary. Again, there's no single best matrix to quantify functional diversity. So it has been suggested to complement, for example, functional richness with functional deepness and functional divergence in that sense. So these are the different trait databases if you're interested to. For example, for amphibians, we have AmphibIO. It's a global database for amphibian ecological traits. So it's a nice database. It's a comprehensive database. So for my thesis, most of my traits came from Southeast Asian bat database. It's a good database as well. So to give us like a total overview of how to calculate these different metrics, this is the workflow for assessing functional diversity in a multidimensional functional space. So this is from the work of Belliger at 2016. So first we need to have, of course, biological data, ecological data. So it's either in terms of the presence or absence, in terms of either abundance or number of individuals or biomass. And we will link that one with its functional traits. So the traits being chosen depends on what kind of question you are answering and of course your expertise. So which functional traits to choose, how to measure them, and how to code them on your data set. So when you already link these two matrices, then we will build a functional space. So when we say a functional space, it just means it's like an ordination. We try to ordinate this different set of species with respect to their different traits. So there are lots of approaches for that. For example, you can use Euclidean or Lower's distance. It depends on the type of data that you have. For example, if your data is a combination of a categorical data and a continuous data, it would be best to use this lowest distance in this ordination process. So once you have that, once you have created the functional space being occupied with that assemblage in a community, then we will link that one in your species data and create these different functional diversity matrices. So this can be implemented in R. If you're interested, you can search the work of Billiger for that. So in here, there are lots of different entities. For example, although it's not clear, functional richness, functional evenness, functional divergence, functional specialization, and as well as you could also compute complementary functional dissimilarities. For example, you have these two communities. To what extent the functional diversity of your two communities differ or similar? So it's just a matter of like an overlap, functional overlap of your two communities. So that's the idea of functional diversity. So aside from taxonomic diversity, which is quite idiosyncratic, we now have this functional diversity which could add another layer for us to better frame what's the impact really of converting forest to oil palm or other agricultural plantations. So another facet that we could look into is phylogenetic diversity. So it's diversity arising from differences in species lineages based on their evolution. So for example here, we have 3 species. So in terms of species richness, we could say that it's the same. They have 3 number of species. But in terms of phylogenetic diversity, the first is more diverse. Now it is being represented by a more distantly related lineage as compared to the second one in which the species of your community is closer related. Now it is clustered. So this is another instance that we didn't capture when we focus solely on taxonomic metric. So getting a phylogenetic tree, these are some of the resources can either be in Newick or Nexus or tree files, and you could download it here from, for example, sequences from GenBank. You could do some alignment and tree inference from Mega and Beast for Bayesian approach. We have Phylomati and other databases. So in short, these days it's really not really difficult to access all these information and resources. So these are one of the main metrics for phylogenetic diversity. We have PD, phylogenetic diversity, mean phylogenetic distance, and linear neighbor distance. So these just some of the measures that are frequently used to measure phylogenetic diversity. But then again, just like functional diversity, there's no single best metric for that. So we need to use some complementary metrics. So state of the field. So you're given with this particular response. The question is, does this response only arose because of chance? Baka nagkataon lang. So for us to really assess that it's not really by chance, I mean, that's really the response. We now have this another state of the field. Actually, you can also use this one in taxonomic and functional diversity, the use of null models. So the goal in constructing a null model is to ask what distribution of values is expected for a focal set of species in which there is no phylogenetic structure, but in which all other properties, that is species richness, are the same. So you are constraining the parameter of interest and let all the other change. So 2 main classes of null models have been used, particularly for phylogenetic diversity. First is the focal set of S species. One can take repeated rows of S species chosen randomly from the regional phylogenetic tree. In essence, this is like shuffling the species identities randomly among tips in phylogenetic tree. So you have this phylogenetic tree and you're just reshuffling the species and the tips. And then alternatively, with the species by site data matrix, one can repeatedly shuffle the species presence among sites to essentially randomize which species co-occur while retaining each species frequency across sites. So it's the frequency that you are constraining. So most of the null models in phylogenic diversity use the first approach. So in essence, we have this community data matrix, and we have this tree, phylogenetic tree. Then out from that, we need to link these two sets of data, and we can generate sets of phylogenetic diversity values. So for us to assess if these values only arose by chance, or that's really the response, we need to create a null model. This is a separate set of analysis. And compare, so you have these observed values, and you have null values, and compare the degree of deviations between these values. So we have this quantification of standard effect size, or SES. So this is now the deviations of your observed and with respect to your null values. So in phylogenetic diversity, that's the equation. Standard effect size is the values of observed minus the values of null over the standard deviation of your null values. So for us to interpret that, positive values means there is phylogenetic clustering. So when you say phylogenetic clustering, your species in a community are conserved. They are closely related. Negative values means over dispersion. So the species in your community is dispersed across the phylogenetic tree. So a value that is close to 0 means it's just a random event. Phylogenetic clustering, co-occurring species are more closely related than expected by chance. Then phylogenetic evenness, or over dispersion, co-occurring species are more distantly related than expected by chance. And we have random patterns in which your observed value and your null value is quite similar. There's no large deviations. This is how does it look like. So to put that into context, here's a case study. This is my master's research. It's on the influence of tropical lowland rainforest transformation systems on taxonomic, functional, and phylogenetic structure of terrestrial fauna in Sumatra and Palawan. So my advisor is Professor Limalibot, and this project is jointly implemented by Göttingen University and University of Jambi, and of course the University SCI for my fieldwork in Palawan. So the idea here is, now in Sumatra, Indonesia, as well, and for example in Palawan, Philippines, you have this tropical lowland forest and intact forest, and you have this jungle rubber. So by definition, we see jungle rubber. It's an advanced secondary forest with a rubber within. It's an agroforest. And then we have rubber plantations, monoculture, and monoculture open plantations. So when you convert forest into these different sets of land use systems, what would be the response in terms of taxonomic diversity? How about functional and phylogenetic diversity? Is it the same, or does the magnitude of response is the same, or maybe is it more pronounced in functional, or maybe it's more pronounced in phylogenetic? So that's the idea behind this research. And also, we are trying to find out, having these three different facets of diversity, we're trying to find out what's the conservation value, for example, of agroforest. For example, it harbors a comparable level of diversity at these 3 dimensions with that of the forest. So we can say that maybe it's in a good state somehow. So in terms of species richness and composition, we can see here that so forests are in green, opam is on maroon, so you can see here a number of species could not be found in opam plantations. And there are also other species that could be found in opams that was not detected in forests. So there's a gradual decrease in terms of number of species. So most of these species are like the forest specialists that are already absent in these transformed habitats. Now in terms of diversity, so this is species diversity based on exponential Shannon index, effective number of species, or the Hill's number. So when we in reference to the OPAM, when we convert species diversity between the forest and the OPAM, we could expect the magnitude of reduction of diversity is about 83%. So it's quite large. When you convert forest to OPAM, the number of species being lost is, the amount of diversity being lost is about 80%. So when you convert when you compare advanced secondary forest with rubber to all palm, it's about 78%. So in here, we can really, sense what's really the impact of converting forest to all palm with just this taxonomic diversity. So in terms of functional diversity, the trend is the same. In terms of functional diversity, all palm has the lowest value. And you can see here the large gap between these forest and all palm plantations. In terms of these different functional diversity at multi-dimensional scale, so the whole area here is the functional space. So when you convert forest to all palm, it shrinks. When we look at the functional evenness, you can see that the functional traits are being represented by just a single species. There's a large circle in there. So by just looking at this graph, you can really see how functional diversity responds to all palm conversion. In terms of functional overlap, when we assess functional diversity of forest and jungle rubber, the overlap is quite large, meaning the functional diversity in the jungle rubber is quite comparable with that of the forest. But in terms of forest versus all palm, there's a complete separation. So I can't emphasize more the impact of all palm. So in terms of phylogenetic diversity, so the same trend, forest, you compare forest and all palm, there's really a large gap. And the left graph is for in Indonesia, the right graph is in Palawan, and we could see that throughout these different regions, the trend is the same. You can see how deparpate the all palm is. So now in terms of net relatedness index, so there comes now the null model, comparing observed phylogenetic diversity with the null model. So we can see that forest and jungle rubber at both sites tend to be more over-dispersed as compared to those monocultures, rubber and all palm, which is more clustered. So meaning, if we look at it at phylogenetic tree, when we convert forest to all palm, now you can see here that most of the representative species in the community are closely related to each other. So you can see that there's somehow like a habitat filtering going on. So when you convert forest to all palm, only a few species could thrive on that. Only a few traits could thrive on that. And those species are closely related. So rainforest transformation to all palm has a significant impact on biodiversity at multiple dimensions. That's very clear. So conversion of forest to all palm led to simple, species poor, and less diverse communities. It led to a marked reduction of functional diversity and a loss of evolutionary distinct lineages. So what can be done? So what? We have these ecological results, and how can you cater this one into policy arena, which the action is being there. So banning all palm is not the solution. So we're saying stop all palm production and all, but it's not the solution at all. So bear in mind that 1 ton of palm oil only utilize 0.26 hectares of land. So when you ban all palm and replace it with another sources of oil, which requires a much larger area of land, so that would mean more forest conversions to these particular crops. So the solution to mitigate biodiversity loss out from this all palm development. So effective policies and programs are needed to stop the clearing of tropical forests for new all palm plantations. And this is the problem here. For example, in Sumatra, the government is not really straight in imposing or setting aside a particular area for plantations. Now, when I was there, a new forest has been converted into all palm, and a month after that, there's this big haze going on, international issue, decrease. It's because of this burning and clearing of forests. So, in terms of policies, for example, if I am the importer of this product, palm oils and its derivatives, maybe I could impose policies in which, although it's happening now, for example, the European Union imposed policies that all palm should not be used in biofuels. All palm should only be used in food products instead of non-use products. Since to limit this demand-driven expansion. For us, the growers, the importers, Southeast Asian countries, Philippines, Malaysia, Indonesia, what could be done is, in existing palm plantations, producers should manage their land more responsibly. So, better management of set-aside areas identified as important for biodiversity and carbon. So, we have these open plantations. There should be a nearby forest patch that is identified by a pool of experts, national expert, that is important for biodiversity and important for carbon stocks. Although it's not operationalizing currently, but that's a good move. So in short, banning all palm could worsen the situation. So future perspectives out from this. So applications of integrating multiple dimensions of biodiversity in ecological and conservation research is a highlight. So I need to highlight that since now it will give us a better understanding of the link between the environment and ecological attributes, ecological functions, and evolutionary histories. So not just a mere number of, we need to explore more, or we need to understand biodiversity response more than just the change in the number of species. We need to delve more into other dimensions. The response of these dimensions are subtle, but it is very relevant. So, for example, its applications is reassessment of biodiversity hotspots, as well as reassessment of protected areas for conservation planning. So, for example, the question is, does our protected areas capture its different dimensions? Or even taxonomic diversity. Like, does our protected areas capture this a large number of taxonomic diversity? I don't know. So, maybe we could delve more on that and assessing our protected areas and incorporating these different measures of diversity to better quantify the impacts of these store plants. So, for example, when we convert forest to agriculture, you have this different response and species switches and abundance, but that response is idiosyncratic. So it's taxa-based. So maybe we could employ these different facets of biodiversity for us to better frame the impacts really of forest conversion and to understand overall drivers of biodiversity. This is rather more on highly ecological. So for example, it's a paradigm now that biodiversity has a positive impact on extreme functions, and for us to understand that to what extent, what are the major mechanisms for this, for us to understand that we need to incorporate these different dimensions. So taxonomic, functional, and phylogenetic, as well as genetic diversity. So at least you learned something. I hope you learned something new today, and thank you. That's all.